Each part of the nephron has a different role in the overall function of the kidney. This module will be an overview of the different roles of each segment of the nephron. The detailed mechanisms of how each function is accomplished will be covered in separate modules. The glomerulus and Bowman's capsule are responsible for filtering blood, such that only certain substances are allowed to pass through the nephron. This is called glomerular filtration. Let's take a closer look to see what kinds of substances can enter a healthy nephron. In a healthy nephron, components of blood are filtered based on size and charge. Cells and proteins larger than albumin are too big to pass through the filter. Smaller proteins, like kappa and lambda fragments of immunoglobulins, are freely filtered. However, small negatively charged molecules such as bicarbonate, chloride, and phosphate are allowed to pass from the blood into the filtrate. Other substances that enter the lumen of Bowman's capsule include water, ions, glucose, urea, amino acids, and some drugs. The substances filtered by the glomerulus make up the filtrate. The first segment of the nephron is the proximal convoluted tubule, which we also refer to as the PCT, and is the nephron's main site of reabsorption. In normal physiologic states, approximately 65% of water, sodium, and chloride are reabsorbed at the proximal tubule. Approximately 100% of bicarbonate and glucose, and approximately 80% of phosphate is also reabsorbed proximally. To more variable degrees, potassium, magnesium, and calcium, as well as urea and amino acids, are absorbed. The proximal convoluted tubule is the only site of reabsorption for glucose and amino acids. Finally, hydrogen ions and ammonia, NH3+, are secreted. Reabsorption is driven by gradient differences between the filtrate and the blood. Since solute and water is reabsorbed, the filtrate delivered to the next nephron segment is isotonic, meaning the same tonicity, and approximately 1/3 the volume. The next segment is a loop of Henle. The loop of Henle's role, with the help of the vasa recta and countercurrent exchange, is to concentrate the filtrate and the interstitium. The loop of Henle is responsible for absorbing approximately 25% of filtered ions and 20% of filtered water. The thin descending limb is highly permeable to water and minimally permeable to ions like sodium and chloride, thereby concentrating the filtrate. This means a high percentage of water is reabsorbed from the tubule, and much of the solute, like electrolytes, remain in the nephron lumen. The thick and thin ascending limbs are impermeable to water, meaning no water can be reabsorbed from the lumen. The thin ascending limb is permeable to ions. In the thick ascending limb, sodium, potassium, and chloride ions are actively transported by the sodium-potassium chloride cotransporter, NKCC2. The NKCC2 channel is one of the most well-known transporters as is blocked by loop diuretics. This cotransporter is responsible for concentrating the interstitium, creating a concentration gradient between the interstitial medullary space and the filtrate, which we will call the medullary concentration gradient. This concentration gradient enables passive water reabsorption from the distal portions of the nephron. The importance of this will become more clear when we discuss antidiuretic hormone, ADH, aquaporins, distal nephron urine concentration, and water handling by the kidney. The distal section of the thick ascending loop of Henle, prior to transitioning into the distal convoluted tubule, is the macula densa, which is specialized cells that interfaces with the afferent arteriole, forming the juxtaglomerular apparatus. The juxtaglomerular apparatus plays a key role in extracellular volume management through tubular glomerular feedback and the renin angiotensin aldosterone system. Upcoming modules will cover these features in depth. The distal convoluted tubule, situated between the thick ascending limb and connecting tubule and the collecting duct, participates in fine-tuning of the filtrate. The DCT plays an important role in the reabsorption of sodium and chloride, bicarbonate, magnesium, and calcium. It is the site of the sodium chloride cotransporter, also known as the NCC, which is the site of action of thiazide and thiazide-like diuretics. While less known to some, the DCT also has some aldosterone sensitivity and ADH-mediated water reabsorption, similar to the cortical connecting tubule and collecting duct. Further fine-tuning occurs in the cortical connecting tubule and collecting duct. Here, water, sodium, chloride, bicarbonate, magnesium, and calcium are reabsorbed, while potassium, hydrogen ions, and urea are secreted. Furthermore, this is the site of action of hormones ADH and aldosterone. ADH is a hormone responsible for determining how concentrated or dilute our urine is. This region of the tubule is impermeable to water except in the presence of ADH. ADH-mediated water reabsorption is also found in the distal convoluted tubule. Aldosterone is a mineralocorticoid released by the adrenal glands in response to angiotensin II, thereby influencing sodium and bicarbonate reabsorption and potassium and hydrogen secretion at this site. Mineralocorticoid receptor agonists are a common class of potassium-sparing diuretics that act at the site of the mineralocorticoid receptor. There you have it, an overview of nephron function.